Hello, everybody. Hi, my name is Aimee Sutton. I'm a product manager for System Test Generation Solutions at Synopsys. I'm here with my colleague, Xiaolin Chen, and we're here to talk to you about combining dynamic and formal verification techniques to improve the overall quality of your RISC-V processor IP. So I represent the dynamic side of this partnership. And when we talk about dynamic methods, we're referring to the process of applying stimulus to the design under test and then observing its response in either simulation, emulation, or FPGA prototyping environments.
Well, hi, everyone. My name is Xiaolin Chen. And when I talk about formal technology, what comes to mind? Maybe not the same as you think, some of the designers may be thinking what it is. So what I'm referring to formal here is really the formal property verification, where the mathematical analysis is used to check whether the design satisfies the functional requirements, right? So formal is exhaustive, and it's very efficient at exploring the corner case scenarios and very good at finding bugs, finding counterexamples, right? Formal has been around, and it's been a necessary step in process verification flow for a very long time. In fact, all the CPU, GPU, or some other PU companies all have allocated dedicated formal resources to be in their verification flow, applying the formal technology. And today, and I think formal is one of those fast-growing applications in the verification flow.
All right, so let's start by understanding the problem that we're trying to solve. Why is RISC-V processor verification a challenge? Well, the flexibility of the RISC-V ISA enables the creation of specialized differentiated processors. However, it's important to realize that each design choice that you make has an impact on verification. Another consideration is that RISC-V has opened up processor development to a wider community, some of which may be experienced in design verification, but not necessarily in design verification of processors. Processor verification methodology is also a challenge because historically, these techniques have been confined within specialized organizations. Finally, tool selection. So there are a variety of open source and commercial tools available that can help you with the verification task. And it's important to consider the benefits and trade-offs of each of them when you're choosing the right one for your project. So there's a lot to think about here, but hopefully this presentation will give you a bit of some new ideas to give you a bit of a head start. Okay,
when you look at a RISC-V verification, we kind of put there, people will say, oh, simulation and formal, there's a vertical view, and we thought we'd give you a different view. This is horizontal view, a parallel processing in a way. So we've divided this RISC-V verification into different focus areas or different hierarchy, different scopes, if you wish. So within each area, we will describe in the following talk how dynamic and formal or formal can be employed and where, right? So first, let me start from the bottom, from the foundation, the unit level. Here is where very formal is very effective, where you can start a verification early and then find the bugs early, and it will be easier to debug at the unit level because it's easier to control, easier to observe, and that from that point of view. And also, sometimes you don't really build unit level test benches in simulation. So this is where formal can really go there and exhaustively explore the legal space and find the corner case scenarios, right? And then look at the RISC-V core block diagram. So you see these color-coded, the 7 blocks, really, it's really cool. So they are identified as well-suited for formal, where you can build a unit-level formal verification environment for these blocks to verify the functionalities. You can build a formal test bench with SVA assertions and auxiliary logic to make sure that to set up assertions and assumptions of your environment. Then you use formal tools such as Synopsys VC Formal, the FPV app, formal property verification app, to verify these design functionalities. So there are some examples examples I listed here, right? For the prefetch buffer, you can build an environment to check for different functionalities, such as actions, how actions are taken in the priority order, where it's coming from different components, and so on. And you can also check for the instruction cache functionality in the branch target buffer dispatch, as well as other functionalities such as resolving the dependencies. And also you can use formal to check the decoder functionality, such as undefined instructions and so on, right? And also in the load store unit, you need to make sure that addresses are always sent before the data, so things like that. And some of the simple ALU functionalities can also, from the execution unit, can also be checked with formal. Then if you go through this whole pipeline, right, going from this instruction issue all the way to retirement, there is a whole pipeline going through control logic, and that is also a sweet spot for formal, where you can check the functionality there. So, and then, yeah, we can go to the next slide. And then looking at the blue boxes, where you can see, there's a lot of arithmetic units, right, such as multipliers, dividers, you're doing the dot products and so on. And these elements can be exclusively exhaustively verified using the formal data path validation, such as on the top it says a DPV app. These apps are very efficient at verifying data path as well as arithmetic instructions, how they compare to your RTL against if you don't have a C model or C++ model, there is such a prepackaged model of arithmetic instructions that you can compare against your RTL to make sure that they meet the standards like M, F, or D, or some standards. Then you can you just need to map the reference model to your RTL, and the app will check that all the arithmetic functions are working as expected.
Okay, the second focus area we're going to talk about is ISA, or architectural verification. So this concerns correct implementation of standard RISC-V extensions. For ISA verification, we have both dynamic and formal techniques that can be applied. So a proven dynamic methodology for ISA verification involves generating stimulus and applying the same stimulus to both the processor RTL and a reference model of the processor. And while this stimulus is being processed, functional coverage can be continuously sampled. Achieving 100% functional coverage while continuously comparing with the reference model will give a high confidence that the design is correct and that the selected RISC-V extensions have been correctly implemented. Creating the coverage model is a significant task. However, since it's defined by the RISC-V specification, it's common to all implementations, meaning you don't have to write it from scratch. There are open source and commercial offerings for RISC-V ISA functional coverage. And it's worth mentioning that this methodology can be used from simulation to emulation and FPGA prototyping platforms. So there are several different approaches to simulation-based verification at the architecture level. The response to the test stimulus can be compared post-execution using a trace file. However, the most efficient and comprehensive methodology is to compare architectural state at the retirement of each instruction. This is a methodology known as lockstep continuous compare. The benefits of this approach include finding errors faster. So there's no need to run the full program to completion, only to find that an error or a mismatch occurred after only a handful of instructions. It's also easier to debug when your simulation can automatically stop at the point of first error. When it comes to stimulus generation, there are several options available. For example, there are architectural compliance test suites available from RISC-V International and other sources. But achieving architectural compliance doesn't mean that your implementation is free of bugs. The verification state space for a processor is very large, and so an intelligent approach to stimulus generation is needed. Right? Pure random generation would be impractical. So what we need is a stimulus generator that mixes constrained random with directed code fragments that target interesting scenarios. Using such a test generator can produce ELF files. And ELF files are inherently portable, so that allows you to reuse the stimulus across different platforms from simulation to silicon.
Now, Aimee has talked to you about how dynamic simulation can be used to verify the ISA compliance. Now I'm going to talk about using formal to also check for ISA compliance. So why do I want to do that? Why do you want to do that? So yeah, maybe anybody has the answer for that? The answer is really that the bug is, the purpose of verification is to find as many bugs and as early as possible, right? That's why, and that's where formal is really good at. And companies like Synopsys, we have these pre-packaged out-of-the-box assertion IP. AIP is not API, so it's an assertion IP. So that you can use as a package that is written in formal, and with very little effort, I think you just need to bind to the interfaces such as instruction fetch and memory interface, data memory interface, and instruction retire interface, as well as register write interface, and with some minimal access to a small number of points along the pipelines and so on to observe some certain events. So all of the properties and policies that's needed for checking the instruction architecture are all included in the AIP, whether it's single issue, multi-issue, in order or out of order, execution, and so on. All this is included in the VC formal RISC-V AIP. And you can use with a property app, FPV app, to verify the ISA compliance. Now, the next slide really is showing some examples that we found with the RISC-V AIP. Where do we find these bugs? These are the open cores that you download. You can download from GitHub, or you can download from open hardware and so on. These are pre-verified with simulation. And these bugs were found. Some of them are pretty obscure. So if you try to do this from constrained random simulation, you may or may not hit it at all. So the possibility of, like the red ones, so the possibility of hitting in simulation is quite rare. And then we just hooked up the AIP, and within 20 minutes, we uncovered this one bug, right? And the other ones may be easy to find with simulation, and then some of them may be in the medium level. You can find them in simulation. But the point is that you do combine the formal and the simulation. You actually find more bugs and faster in that way. The other thing I want to mention earlier in the earlier slides, we mentioned that there is a security verification. So there is a formal, also has a security verification app that's called FSV, where you can use to check for, it's another out-of-box solution, where you can check for data leaks, whether you can go from a secured region to an unsecured region, and so on, leak to the unsecured region. You don't want that to happen. So, so that you can use an app for.
Okay, so now let's talk about the problem of verifying custom instructions and CSRs. And again, here we have solutions in both the dynamic and using formal methods. So the same approach to architectural verification that was previously discussed can also be applied to custom instructions and CSRs. The main requirement to do this is to have a reference model that is extendable to allow verification of custom features in addition to the standard ISA. This diagram gives an example of such a reference model from Synopsys, which supports the configurability defined by RISC-V and is extendable. Okay. Another requirement is that the test generator and functional coverage model should also be extendable so that you can know that your custom instructions have been thoroughly exercised. Achieving 100% functional coverage of custom instructions and CSRs will lead to high design quality using dynamic methods.
Okay, so formal, again, also offers a register verification solution, and this is like a formal register verification app, and that is another out-of-box solution where you just take the register specification, and then whether it's in IP exact or raw format, you can use some of the out-of-the-box assertion IP again, such as UMBA AXI and so on, to check for register access against this specification when it goes through the standard protocol. And also, Aimee talked about the customer instructions and so on. And in that case, you can add more, create more formal properties and so on in your RISC-V AIP setup. And also, in the case of custom instructions, for example, you modified you deviated from standard, then you can use a sequential equivalence checking in formal to make sure that your custom instructions, your modifications did not break any functionality that not supposed to be affected, not supposed to change. So that is also a common usage for sequential equivalence checking.
Okay, the last area we're going to discuss is the processing subsystem, which can include many core architectures with shared memory. And here again, there are both dynamic and formal approaches to this problem. So memory systems can be complex, and exercising them to a high degree of confidence is a significant challenge. The key to using dynamic methods for memory system verification is having a test generator that is aware of the system and memory architecture and can generate interesting and stressful scenarios, such as true sharing and false sharing scenarios. For multi-core systems, hardware emulation becomes a requirement, as simulation would be way too slow. Right? Combined with emulation, novel techniques such as on-platform generation have proven to be effective in finding corner case bugs in cache and memory coherence. So the process of on-platform generation involves a rapid cycle of test generation, execution, and checking on the design under test itself, enabling many tests to be run at high speed and to quickly traverse the state space to find bugs. Another dynamic approach to verifying large designs involves the use of an FPGA or a prototyping platform. So in this scenario, the synthesized design executes the test at hardware speed, while trace data, which contains changes in architectural state, is dumped to a file or database and then streamed to a connected host machine. The data can then be checked for correctness by comparing the state against a reference model. In this environment, longer and more intensive test programs can be run, including real software such as booting Linux.
And also, there's another way of using VC formal, the FPV app to verify cache coherence. So this is why quite common people actually build a formal test bench, again, using properties and logic to be able to build the constraints and the checker properties to thoroughly verify the cache coherence. And it's challenging because formal gets state explosion and so on. So maybe it's difficult to get full convergence on these kind of properties. But whatever you write, all these assertions and assumptions, they're not wasted. They can be fully utilized in your simulation run to be able to catch bugs there. Right.
Right. OK, so in summary, there are many benefits to adopting a combined dynamic and formal approach to RISC-V verification. And choosing the right tool for each unique problem can lead to a reduction in your overall verification schedule. Starting out with unit-level testing using formal verification enables earlier bug detection and easier debugging. As we move to the ISA level, custom instructions and processing subsystems, dynamic and formal techniques can be used in parallel, complementing each other by finding different types of bugs. Overall, by employing a combination of different techniques, we can shift the verification task earlier in the development cycle, and by finding bugs earlier, achieve higher quality RISC-V processor IP.
Well, that's the conclusion of our presentation. Well, thank you for your attention.
I think we have time for one question. Anyone would like to ask a question? Hang on.
By the way, if you have any questions, we have a booth there. We will be there. We'll be happy to answer any questions you have, discussion in detail as well. Sorry, go ahead.
Regarding the architecture or ISA verification formally, you mentioned that a user needs to bind the assertion IP with the RTL. Does this mean that a user needs to manually map CSRs?
No, you don't need to. No, that's not for CSRs. This is the CSRs. We just use your IP exact file, right? We just need that file.
So verifying CSRs is not included while verifying ISA. This is what I understand, right?
The ISA compliance, how the instructions work, and that is a different assertion IP, right? Assertion that registers itself, access itself, is a different kind of app.
So without considering the effect of instructions on CSRs,
right?
This is nothing. Okay, thank you so much.
Yeah. There's two different apps to
Sure,
verify that. Yeah.
Okay, I think that's it. We are on time, so thank you very much.
Thank you.
Yeah.
Thanks, everyone.
Thank you.